Good afternoon. Welcome to the course Thermodynamics of Materials. Today we are into lecture 155 and 156. Today we will discuss or take up assignment number 12. We will deal with some problems involving phase diagram and solution thermodynamics properties. So these are the three problems I have already written. Already, actually, I am showing there 1, 2, 3 problems, and there is the fourth that will, after we have completed these three problems, solve these three problems, then I will take up the fourth problem. So let us start without wasting time. The first problem let us read on. This AP is solution 1. Problem 1, solution. This solution, this phase diagram, see, let us read this problem quickly. The APS phase diagram indicates that iron and sulfur, before I forget, actually, I tell you one thing, these problems are taken from D.R. Gaskell's book, Introduction to Metallurgical Thermodynamics, okay, in the second edition. Oh, I forgot to write that. D.R. Gaskell page, second edition. This is second edition. Second edition, okay. By D.R. Gaskell. So let us read this problem. Okay. These are all exercise problem. Okay. So read this problem. The iron sulfur phase diagram indicates that iron and sulfur are completely miscible in the liquid state and are virtually immiscible in the solid state. The liquidous composition at 1200 degrees centigrade is 62 mole% iron and 38% sulfur. The heat of fusion of iron at the melting temperature of 1535 degrees centigrade is 15,360 joule per mole, and liquid iron has a heat capacity that is 1.3 joule per Kelvin per mole, higher than the heat capacity of solid iron. First, question is, first part of the questions is derive an expression for the free energy of fusion of iron, delta G0 M for melting, delta G0 melting as a function of temperature. Second question is calculate the activity of iron in a liquid solution of iron and sulfur in which X iron is 0.62 at 1200 degrees centigrade. Third, assume that the liquid iron sulfur system is regular, because it means regular solution, and calculate the activity of iron in the liquid alloy in which XAP is 0.62 at 1535 degrees centigrade. Fourth is calculate the integral molar free energy of mixing of the solution in which XAP is 0.62 at 1535 degrees centigrade. And the last one is calculate the composition of the iron liquidus in the system. APS system is changed now. Instead of AP sulfur, it is now APS. So what would happen to the composition of, in terms of iron, okay, composition of the iron liquidus in the system is changed to APS at 1200 degrees centigrade. This is the these are the problems, okay, and so let us solve one by one. A first of all. First, before I actually take up this, let me draw the diagram, a rough sketch. rough sketch. Okay. This is your liquid, this is your iron, this is side is sulfur, XS. Moving to this, what is this composition? This is actually, so this composition is, which is actually what? Composition is asked 0.38 sulfur, okay? So this is 0.38 XS, and obviously the balance is iron, XAP is 0.62, okay? This composition, this is at 1200 degrees centigrade. This is the temperature. You just, this 1200 degrees centigrade is nothing but is 1200 plus 273 is 1473 Kelvin. So this is, if I write in terms of 1473, I'm very sorry. These are given also. They are actually 1848. Actually, the melting points of this actually 1808. Oh, this is the melting point of iron 1808. And melting point of iron is given is 1535 degrees centigrade. Is given here 1535 degrees centigrade. Is that is plus 273 is 1808 Kelvin. This is 1808 Kelvin. This is what temperature? This is what temperature? This is our interest. Is 1200 degrees centigrade, means 1473 Kelvin. This is the liquidus. Composition is what? 0.38 mole fraction sulfur, okay, or 38% mole percent sulfur, and the balance is 62 mole percent iron. So this is the actually diagram, and what is here, you can balance this now, you can label this. This is nothing but liquid plus sulfur, and this is sulfur, this is liquid plus iron, and this is iron plus sulfur. They are immiscible, completely immiscible, and virtually immiscible in the solid state. So pure iron plus pure sulfur. This is the phase diagram. Okay. Anything else? Okay. No, it's okay. So okay. So this composition is this. Okay. So now take up one by one. A. A. Okay. That's right here. A. What is, first of all, try to create delta G0 melting. For the delta G0 melting, free energy of fusion, delta G0 melting is what? You know, okay. Delta G0 melting is what? I would say delta H0, delta 0 melting of iron, melting is what? Del iron of iron actually. Melting of iron, okay, minus melting of iron. Delta G. So from which actually it is better actually. I should write. So for the timing you write this. Delta H0 melting is Ts delta or at T is Tm. Right, you better write this. Then at T is Tm. Delta G0 melting. Delta G0 melting is 0, which gives you, this leads to what? This gives you delta S0 melting at temperature Tm is nothing but delta H0 melting at Tm over Tm. Okay. T is Tm and these are delta H0 melting Tm and delta S0 melting Tm. Okay. What is this value? This is given as 15 is 15360 over what is the temperature melting point is for iron. This is iron. Remember, for iron. Okay, this is giving for iron. So what is the melting point? 1808. What is the entropy? Then comes as entropy change. Entropy of melting is actually 8.5 joule per mole Kelvin. Okay, 8.5 is 8.5. So this is giving this now as a function of temperature, delta G0 melting. So this is given delta G0 melting as a function of temperature. So T is what? You write this again, delta H0 melting T minus T delta S0 melting T. What is this? You have what value? Delta H0 melting is given here. You write somewhere. Is this this one? This is actually delta H0 melting at Tm. So delta H0 melting at Tm, melting at Tm. So Tm is, what is the Tm? 1808. I'm concentrating on this term. So this Karkov's equation, 18, this temperature and this temperature. This temperature is known. Tm is, write a melting point iron, Tm iron, right? Tm iron, melting point of iron. So this is 18, mine is plus, we call delta Cp dt. So you get this, and that must be integrated between what temperature? 1808 to T. So this is the first term. You know, for 1808 the value is given 15360. That I will substitute, but you know that. So make that as a reference. 1808, this is T1 and T itself is T2, T1 to T2, T1 to T2 delta Cp dt. Similarly, take up this next one minus T. What will be? It is similar relation, only instead of dt it will be dt by T, because this is also similarly delta S0 melting. What temperature? Tm Actually, Tm is 1808, right? 1808. So don't have to, this temperature plus delta Cp dt by T. And what is the integration limit? 1808 to T. Absolutely no problem. Okay, so this is substitute the values. This value is what? This value is what? What is this value? 8.5. What is the delta Cp? Delta Cp, note here, delta Cp is what? See, melting means, melting is what? Iron solid to iron melting. What is melting? Iron solid goes to iron liquid. So what is delta Cp? For this, Cp of delta Cp is Cp of iron liquid minus Cp of iron solid. So this is delta Cp. This delta Cp, Cp liquid. What is this? That is, liquid iron has a heat capacity 1.3 joule or Kelvin per mole higher than the heat capacity of solid. So this difference is delta Cp is given as 1.3. Can I write 1.3? And here also likewise 1.3. And what is this value? Delta 80 is okay. What value this is? Actually, I am writing another line. Instead of here is what value? Write 15360. It is better. It will be clumsy. You know, it will be clumsy. So it is better I write once more. Another line. So write this. Substitute this value. 15360. Happy? Plus delta C. Write this. 1.3 integration 1.3 dt 1808 to T over minus T, right, again right here 8.5 plus integration 1.3 dt by T. Temperature is 1808 to T and no problem. Okay, so this simplify this 15,360. This is actually joule per mole. Okay, so that I will write at the end 15,360 plus 1.3 outside T minus 1808. Okay, and then what you have? You have third bracket here minus, you get a T here outside 8.5 plus 1.3 ln T by 1808. I think this is all set. Okay, so if you actually want to break another break down into another line is 15,360. Let me write here 15,360 plus 1.3T minus this is 2350. You check this. So this part is over. This part is over. Then it is minus 8.5T, and then you have minus 1.3 T ln T. First term T ln T, and the last term is plus 1.3 T ln 1808. Okay, 1808. Okay, so plus 1. This T is T here 1.3 T, this minus and this minus plus ln 18 is okay. So this gives you, all right, or delta G0 melting T. You just tidy up this one, then you combine these terms is 13010 plus 2.55 T minus 1.3T ln T joule. This is expression joule per mole. Okay, so this is the delta G0 melting. And here X over T as function of temperature, joule per mole. This is the answer. Answer to part A. This is answer expression. Second one, B. Take up B. B says what? Calculate the activity of iron in a liquid solution of iron and sulfur in which XAP is 0.62. Means this is X sulfur is so liquidus. You can write here. You can X sulfur is 0. XAP is this is X sulfur is how much? 0.38 and XAP is 0.62. This composition. So what is to be activity of iron in the liquid solution? What is the activity of iron in the liquid solution? So question is follow. In the liquid solution of iron sulfur, means this is the liquid solution and 1200 degrees centigrade. That means the liquidus, this liquid composition at this point of the liquidus. This is the liquidus. These are the liquidus. This is iron liquidus. This is sulfur liquidus. These are the liquidus and these are the solids. This is the solidus. So here actually this point, that means what is the activity? The question is what is the activity of iron here in the liquid phase? In the activity iron both of iron and sulfur in this liquid solution of this composition at this temperature. That means this point. What is the activity? So okay, better I should not. It's okay. So what is this activity? One thing I tell you what. First of all, you may tend to write. Okay. Activity. Okay. This. Okay. So this is fine. Very good. What is this? What is the activity here? Liquid. So what you apply this one, this principle. I tell you. You know, at this. Suppose I ask you, what information do you have at this composition? At this state. What is the state? That is a liquid with composition 0.38 mole fraction sulfur and 0.62 mole fraction iron at a temperature of 1473. And if you ask me pressure, you know this phase diagram is drawn for 1 atmospheric pressure. So that is also known. So what is the activity of iron? Take up one by one. Then you take up actually the activity of sulfur. No, activity of iron is required, not on sulfur. Activity of iron in a liquid solution of iron and sulfur. This is a liquid solution of iron and sulfur, obviously. Okay. So, what is your idea? What information, what knowledge do you have about this state? What knowledge? In terms of activity of iron. What? You know one thing. So this liquid, it is in equilibrium with iron, pure iron, solid. So activity of iron at this state is 1 with respect to solid iron as the standard state. But this question is asked actual activity of iron in liquid, in a liquid solution. So it is actually the question is it is to be understood with respect to liquid iron as the standard state. What is the activity? That is actually expected, and that is implied also. The activity of iron in liquid solution is with respect to liquid iron as a standard. With respect to solid iron, purely 1. Anyway, given that you know the activity of iron in the in this liquid solution with respect to solid iron as the standard state is 1, then take help of this information. Utilize this. Capitalize this information to find the activity of iron with respect to liquid iron as the standard state. So what is that famous relation you never forget, RT ln activity of iron. I will use number of times this relation, that our activity iron with respect to liquid. Let the G0 melt, okay. RT activity of iron with respect to liquid is what? Recall this. G iron solid 0 minus G iron liquid 0. You can give a third bracket on this, plus RT ln activity of iron with respect to solid, means with respect to this standard state. These together, this constitute GFE bar. GFE actually it comes from, recall. How will you get this? Always remember. This is a very nice way to know activity of a component in a given with respect to a certain standard state. When you know the activity with respect to another standard state, you know with respect to solid standard state, your solid iron standard state, so you will utilize this value. Using this value, you get this. Provided you know this. This is of course the melting. Minus delta G0 melting. You have repeatedly used this. And delta G0 melting expression is here. And this whole problem is for this 1473 Kelvin. Second part, 1473, 1200 degrees centigrade. So you use this. So, and how do you get this? Recall, I am writing you. Gi bar is Gi bar. Remember? Gi bar, so I is here iron. Gi iron, sorry. Gi bar is this identity. This express this Gi0 plus RTL and AI. Gi0 plus RTL and AI. So recall, I am writing RTL and AI. So Gi0, this is a so the standard state 1. This is with respect to standard state 1. This assumption which is written here. And right hand side is with respect to 2. 1 may be solid, 2 may be liquid. 1 may be liquid, 2 may be solid. 1 may be Gaussian, 2 may be Hernian. So never forget. So Gi0 to the second plus RT ln activity of I. This always happens, you know. RT ln AI. No, this is not possible. RT ln AI 2. It is manageable. Right. So the same thing. I mean, it is 1 this side. So this is here. I is the say this side is liquid. Say 1 is liquid, and this is actually 1 is liquid. This is this one. 1 again. I is iron. 1 is liquid. So RT ln activity of iron liquid. This plus this Gi0 liquid goes to the right hand side. So this goes to the right hand side as minus, and the other rest is 2 is solid. So Gi0 solid means GFE0 solid. 2 is the solid. So solid plus RT ln A iron. 2 means solid. A iron solid. So you get this. This is known as what? This is known as, remember this relation I will use multiple times in these problems. So I am writing once more, or RT ln a Fe liquid which is required to find is, it is minus delta G0 melting. Remember, melting iron, delta G0 melting. Delta G0 melting. Okay, you can write this iron. Iron liquid delta G0 melting iron is the, for this is given. This is for iron. Remember this I have written here. This problem is about for fusion of iron. Okay, delta G0 melting iron. Okay. Just you can write this delta G0. If you want to write. If you understand, don't write. Too many things cannot be written. Actually, but you made this A melting iron. This is so this is the expression. Minus delta G0 melting. This is the delta name iron. As a T means as a function of temperature. So, but currently we are using 1200 degrees centigrade. So plus RT ln activity of iron solid. Incidentally, you know this answer. What is this value? Follow. At this state, as I have already told, this liquid is in equilibrium with iron or saturated with iron. Solid. In equilibrium with saturated with iron means it is in equilibrium with solid iron. Hence, the activity of iron solid at this state. Just at this state, ask the question properly. What is the activity of iron with respect to liquid iron as the standard state at this state? Answer is this. And use this relation. Answer is this. What you know? Activity of iron with respect to solid iron as the standard state is 1, because it is here, it is liquid is saturated with iron, or you may say it is in equilibrium with solid iron. So this Ln1 means what? Whole thing is 0. Ln1 is 0. So what is the answer? And what is this? This value if you substitute for what temperature? 1473.
Okay.
14 is okay. Let it. Yeah. So substitute T here for what is the temperature? T is right here somewhere. T is given to the 1200 degrees centigrade. I mean this one, this point. T is 1473 Kelvin. So you substitute here, then you will get this value. Delta G melting will be, you get some value. Okay, what is that value? Minus, okay, 2797, and there is a minus here. Minus 2797. Minus 2797. I am correct. Okay, minus delta G melting. So this will be 2797, and minus of that minus 2797. So this is this. Or R is how much? 8.314 R. What is the T? T is how much? T is how much? A moment ago, 1473. Or shall I write here? All right. Or you get activity of Fe liquid. This liquid means here, not in the liquid, not the liquid phase. This is focusing, insisting, or emphasizing. This is the liquid standard state. Pure liquid iron as the standard state. Where this is actually in the system, and if there are a number of phases in each phase, in which phase are all participating phases. So question is, what is the activity of iron? And this L is with respect to liquid iron as the standard state. Here, see, with liquid iron as the standard state, and that is the question. Okay, implied here with respect to, what is the answer? 0.76, I guess. Activity of APL 0.796. 0.796. What is the question? Oh, answer. This is the answer. 0.796 answer. Answer to B. And let's take up the C. C you take up. Okay, C is what? Assume that the liquid iron sulfur system is this liquid solution is regular. Regular solution, not ideal. Regular solution. Very good. Then calculate the activity of iron. Calculate the activity of iron in the liquid alloy. In this liquid alloy, at what temperature? In which XAP is 0.62, means this composition. But at 1535 degree centigrade. 1535 is what? I have given 1535 degree centigrade. Really? At 1535, and melting point is also 1535. Okay, melting point at 1530. Okay, maybe so. Maybe so. Okay, 1535 centigrade. Okay. Achha. 1808. Okay. Melting point. Okay. Very good. So this is where you go top. Question about this state. The liquid behavior is regular. Now you have to use the regular behavior relationship. So you have to recall this, so that you will use. But before this, what you will do, I tell you what. First of all, do activity at what temperature? This one at which temperature? At T is 1473 Kelvin. Let us see. You have to introduce gamma. If you want to exploit the regular solution relation, your T ln gamma is constant for regular solution. So find the gamma value. Activity is this. So T at T is 1473 Kelvin. Refer to the part B. Activity is this. What is the gamma? Iron liquid is what? Kelvin is nothing but activity over mole fraction by XAP. What is this? Right? 0.796. What is the XAP? XAP is what? I will bring that to 1.62. 1.62. What you get for this? 1 point something. Okay. Let us is 1.284. 1.284. So this is the gamma. Which temperature? You may write this. You may write here. So write once more. Gamma iron liquid. This is our liquid. Liquid is I don't have to write. What temperature? 1473 Kelvin. That is more important here. Is how much? 1.284. To find the activity, well, you have to calculate the activity. You first find the activity coefficient, then multiply by the mole fraction. So multiply activity coefficient for what temperature? Well, temperature has changed to 1535 degree centigrade, means this temperature rather than this temperature. So this temperature, not this, but that. Not 1473, but 1808. So what is this? What is the relation? You know, T ln. Recall regular solution behavior. So what is your question? This is given. So gamma iron, what temperature? No, the temperature is 1808 Kelvin. Is how much? So regular solution, recall regular solution behavior. Recall regular solution behavior. Regular solution relation. What is that famous relation? T ln gamma is constant. That means what? That is equal ln gamma Fe. I'm not writing actually. Fe is not, because it is about Fe. Okay, 1808. Okay, right. I'm writing for you. ln gamma T2 ln gamma T2 by ln gamma T1 is T1 by T2. This is recall. So apply this, or hence, it is better I actually stop here. let me write somewhere, just here, just this, here it will be over, don't take this like this, or hence what you can write, ln gamma, iron implied, iron understood, T2 is 1808 over this unknown stuff, ln gamma, which temperature, 1473, is nothing but 1473 over 1808. Now substitute the values, or ln gamma 1808, which is the unknown. This is what ln of what, gamma 1473 is what, a moment ago, gamma 1473 is what, 1.284. Okay, this is gamma, yeah, 1.284. So substitute the value 1.284 is 1473 over 1808. Just remove this line, this line also, or using this, or gamma 1808, if you apply this, you will get what? Okay, so as you increase the temperature, it will be decreasing. So 1.1 or something like this. It is gamma 1808 is 1.225. 1.2. That is, now we write nicely gamma iron. And it is liquid, of course. It is liquid. About this liquid compositions of this liquid you can write. And what else you can write? Gamma iron liquid, and temperature, of course, that is the question, is 1.225. This is the answer. No, this is not the answer, because question is about find the activity of iron, not activity coefficient. If coefficient, this would be the answer. So what is the activity? Hence activity of iron liquid, similarly same things, and activity of iron liquid 1808, you can write this temperature, this temperature 1808 is what? Gamma iron times X iron. So what is this? 1.225. And what is the X iron? X iron is 0.62 times 0.62 is what? This gives you 1.225 times 0.62, 0.76. 0.76. Right? Once more. That is right, 0.76. This box, the whole. The answer to part C. Now next take up part D. Okay. Many things these are all over. Let's remove this. Next is D. These what? Calculate the integral molar free energy. Actually, integral molar in bracket I actually inserted. It was written only free energy of mixing, but it is better specify clearly to the students that it is integral molar free energy of mixing of the solution in which XF is 0.6. At what temperature? 1535 degrees centigrade. This temperature. What is the integral free energy of mixing? So what is required for integral? Tell me. Integral free energy of mixing is what? Delta G excess. Integral free energy of is what? Tell me. Is what? XFE. Tell me. GFE bar excess plus X. What is the other component? Sulfur. G sulfur bar excess. Okay. Now the question is, what is the, write this nicely. XFE what is this? RT ln gamma Fe. RT ln gamma Fe. As a temperature, what temperature is focused? D temperature is 1535 degrees centigrade, means 1808 Kelvin. This is the reference. Okay. So RT ln gamma plus X sulfur RT ln gamma sulfur. The question is, you know the gamma iron. Gamma iron very nicely 1.225. Achha, you remove this. This is actually remove the unnecessary. This is the gamma iron. Gamma sulfur. Again use the regular solution behavior. If you know what is that behavior, okay, gamma iron and gamma sulfur, they are actually ln gamma A is alpha xb square, ln gamma B is alpha x square. Okay, that one. Recall this. So I tell you what RT regular solution behavior. How to get a question? How to find gamma S, gamma AP already know. This is known, already known. Yeah, 1.225. 1.225. So gamma S, okay. Gamma S, how you get this? Okay. Very good. How to find gamma's question? So recall this. What is RT ln gamma? This here we remember. RT ln gamma A is omega xp square. So this is regular solution. How to find regular solution? Omega is the solution parameter. Omega is solution parameter. So use this information to find omega. What is RT ln gamma iron is what? RT ln gamma iron is omega x square, x alpha square. What is R? 8.314. What is the T? T is the temperature 1808. What is the ln gamma iron is what? 1.225. Is omega the unknown solution parameter? XS is obviously XS. What composition we are discussing? D. What composition we are discussing? Same composition remaining the same, okay, all the time. X sulfur is 0.38 square. This leads to, if you do the calculations, remove this solution parameter. Remember this solution parameter. Omega gives you omega as what value? Omega is 21126. Once omega is found, then you take up this complementary relation. Complementary is what? Now RT, right? Gamma sulfur. How to find gamma sulfur? Here writing the RT ln and regular solution behavior. Regular solution behavior. This is the omega is the solution parameter. Okay, RT ln gamma what? Sulfur is what? Similar, exactly similar. Remember, omega is a alpha RT. In case you want to do this, alpha is actually inversely proportional to temperature, and omega is independent of temperature, etc. So very good. So RT ln gamma sulfur is what? Okay, I'm sorry. RT ln gamma sulfur is what? RT ln gamma sulfur is what? Okay, the opposite. Omega x iron square. So do this. What is this? Right, substitute or why? Okay, this is B. Remove this. Remove this. These are all removed. B is already over. Oh, sorry. Actually, anyway, it is seen here. Yeah, actually, composition is seen here. Okay, or quickly. 8.314. The temperature is 1808. ln gamma sulfur is the unknown, omega is the value 21126. If you check this calculation, I did this calculation myself, so I think these are all correct, but even so, you actually check back on this, okay? You do yourself, calculate yourself and check it. XAP is what? What is XAP? Recall this as I told you, 0.62. 0.62, I'll just remove this, okay? This is 0.62, 0.62, written at number of places square. If you do this calculations, or gamma S is what? Oh, RTL and gamma, I'm very sorry, unnecessary. Oh, okay, unnecessary RTL omega x square. RTL and gamma is what? This side, no? This side. RTL and gamma, okay. And this much is, I tell you what, I am taking up. Actually, taking up. It's omega x square. And in fact, you don't have to, omega is already known. 21126 times XAP is what? XAP is what, as I told you, 0.62 square is how much it is? Coming as 0.26 square is, 0.62 square is what is coming? 8126 joule. 8126 GS 8121 joule. Okay, this is done. Okay, see, yeah, this part is done. Yeah, this part is also actually this is better. I didn't give you the value. This is how much? This is how much? This is RTL and gamma iron is how much, and omega is this, because this is how much? This is how much? RTL and gamma is what? 3050. 3050.5. So how do you get omega? This is 3050 divided by 0.38 square. Okay, and you get this. This okay. This is omega. So this calculation is, this is RTL and gamma. So I am writing for you clearly. So as above, from above, I am writing, because I missed this point. Because RTL and gamma iron is all known. R is known, T is known, Ln gamma iron is known as what? 1.225. So this gives you have actually a numerical value for the entire thing. In fact, omega was done, so omega was found. So this was found actually 305. So I am writing here from above and from above, right? So that you have RTLN gamma iron is how much? 3050.5 joule. Okay, right here. This is joule right here. Joule. Okay. So this is I have repeated here. Okay. Once this is done, why I am doing all these things? Because you know this is the delta Gx. This is what you call integral molar excess free energy. Right here. Integral. Question is also integral molar free energy. D is what? Oh, sorry, wait a minute. I made a mistake here. Integral molar excess free energy. Excess. This is not there. Excess free energy of the solution. sorry, not mixing. Mixing is delta GM, and it will be what here? Where it is? You are doing work here. It will be GFE bar M, and it will be RTLN activity FE. Activity sulfide, but when it is excess, it is gamma. So integral because together, okay, as different from partial. Molar for 1 mole, because XAP plus XS constitute 1 mole. So integral, and this for 1 mole, integral molar excess free energy. These are, we call this integral molar, okay, when this XAP and XS are involved, so that 1 mole is addressed. And what is the other thing? Other possibility, integral total when there are Na moles and Nb moles, not Xa and Xb, Na and B, that is total, but we are considering molar. So integral molar is easy. If you know for 1 mole, you can find for N moles, okay, Na plus Nb moles, okay, so no problem. So this is easy deal, this formula. So from above, so you just write here you see corresponding region. Hence, integral molar excess free energy, that is integral molar excess free energy of the solution. Okay, so delta G excess. Hence, delta G excess is what? Delta G excess is what? Tell me. Delta G excess is what? Right? XFE. Write once more, write, copy this, RT ln gamma iron plus X sulfur RT ln, how many minutes?
57 minutes gone. 1 hour 3 minutes.
RT ln gamma sulfur. Just substitute the values. XAP is what? As I told you, 0.62. RTL and gamma iron is how much? 3050.5. 3050.5 plus X sulfur is 0.38 times RTL and gamma S is what? How much? 8121. What is the result? Or delta G excess, another line maybe is what? The calculations, okay, is what? Is this 4977 joule. 4977 joule answer. Remove this clearly. You can see this. This is D actually, D. So remove this. The last is E. Last segment is calculate the composition of the iron liquidus. This is liquidus. This is the liquid iron liquidus. This is iron liquidus. This is sulfur liquidus. You know this, and this is the solidus. Okay. Anyway, liquidus. Iron liquidus is this. Composition of this in terms of iron and sulfur, it is given. How it is given? 0.38 mole fraction sulfur, 0.62 mole fraction iron. Sorry, I am correct. 0.62 mole fraction iron. So this is it. But question is calculate the composition of the iron liquidus in the system. You check the system. APS, not APAS, not AP sulfur, but APS. Then what will be the composition? Means what is the mole fraction of AP and what is the mole fraction of APS? Currently we know in terms of AP sulfur system, we know XAP, XS. So this change. So right, at 1200 degree centigrade. 1200 centigrade means this composition. So we focus on this composition. Liquid iron liquidus means this. In terms of iron sulfur system, we know what, right? In terms of iron, at temperature mentioned also, at here also 1200, 1473 Kelvin. At one liquidus iron, okay, what is it? Iron liquidus. Iron liquidus has the composition which we know, which is given as the composition what XFE is what 0.62 and X sulfur is 0.38 and X sulfur is 0.38. Okay, this you know. Now in terms of Aqueous system, question is XFE for the same okay, this point, same liquid, same state of the liquidus, for the same state I writing same state of the liquidus, iron liquidus, actually you don't have to write too much. Same composition means this point remains the same. That is XFP is this, X is this. Question is what? Question will what? Instead of the same composition, what is XFP is what? XFPS is what? So quickly remove this. Here it will go over. Achha. If you want to solve this type of problem, you consider this. Okay? Consider total number of moles as n of this liquid. This liquid, n moles I am considering. There is no problem. So let us consider. Can I give a star here? Because it is better I use this space. Remove this, no problem, and this is good enough. Let us consider n moles of the solution, n moles of the liquid solution. Then what does it mean? Hence solution. This is Gibbs scale. So solution. XAP is what? Mole fraction is how much? 0.62. 0.62 n mole. I am very sorry. NAP. NAP is what? N moles total. 62 mole. 0.62 mole percent. So 0.62 mole fraction. So 0.62 moles of iron is there. The solution is comprised of and it is comprised of, and the solution is composed which is comprised of of NF is 0.62 and N sulfur 0.38 N. Now this cannot be violated. For this composition, system is now Fe sulfur, Fe, yes. A good analogy is iron carbon diagram. We actually often consider Fe, we consider Fe3C diagram. Fe3C, or you can consider iron carbon. At 6.67% carbon, you can consider it is, this is actually corresponds to Fe3C compound. So, and we can confine our diagram to Fe3C, so that we can get percentage iron and percentage Fe3C. Okay, like this, alpha phase and alpha and cementite, like this. But if you consider Fe carbon, when you graphitization occurs, you have to report in terms of iron carbon system. So this knowledge is very useful. And I am showing you what is the problem here. I tell you what, this problem, this is your 0.5 set, this is 0.38, so this is your 0.5. What is this corresponds to 0.5 x? This is there is a compound. This is APS. APS, mole fraction of sulfur is 0.5. 1 by 2 is 0.5. So 0.5 corresponds to APS compound. So there's a line compound. This is a compound. Now you consider your system is this. Follow this binary, APS binary, not AP sulfur, APS. Here squeeze or restrict in this space, in this span, APS, and this one remains same. This composition, now you cannot say sulfur. What you have to say? Percentage iron or mole fraction iron, mole fraction APS. Follow this. This is the diagram. APS. Okay. And for this composition, at this composition, how much APS? How much AP? So recall this. This is the 0.5. 0.5. Is okay. This is the diagram. So this is your AP3C cementite here. Carbon there. Far away from this. 100% carbon is the carbon, pure carbon. And cementite is 6.67% carbon. Weight percent, I mean. Okay. In here you have mole fraction you are considering. Then you have the concept is same. So 0.2. It's okay. So this is okay. So now comprised of this. Now do one thing. Sulfur balance. From sulfur balance. Sulfur iron is conserved, sulfur is conserved, unchanged. So what is the NS 0.38N is what? NS. Now you have to admit in APS system, NS in APS system, NS is what? The 1 mole sulfur is equivalent to 1 mole APS. 1 mole of sulfur is contained in 1 mole of APS. Same number of moles. 1 mole APS corresponds to 1 mole sulfur. Or 1 gram atom of 1 mole of APS corresponds to 1 gram atom of sulfur or gram mole of sulfur. Same thing. So N sulfur is equivalent to N APS. They are exactly same. 1:1. If is 1 APS. So NS. So you can write very nicely. This is NAPS. You got this NAPS value, but you have to get X APS. But okay, coming to that. Now, what balance is left? Iron balance. What is the total iron? Tell me. 0.62N. That is the total iron. Total iron. Okay, total iron. This is comprised of what? This is total iron. Total iron. It cannot be changed. Total iron. It cannot be changed. It will be now what? Iron is reporting where and where in the APAP system? In both. In iron is there. Iron is present obviously. And in APS, iron is also present. So it is nothing but in number of moles of iron, okay, and number of moles of APS. Because 1 mole APS gives 1 mole iron, and 1 mole iron gives 1 mole iron. So NAP plus NAPS is the 0.62. Now out of which this much is hot, how much? 0.38. What is left here? NAP. This NAP total. No, this NAP in the APAPS system, okay? Now let's check, okay? NAPS, okay? NAP is what? How much it is? 0.62 N minus 0.38 N is 0.28 N. Now take up the last line. What is the mole fraction? Both you have get. What is XAP then? XAP is what? Tell me. XAP is 0.2 N. Its contribution 0.2 N. And what is the contribution of the other one? Is 0.38 N. APS. So 0.2 N plus 0.38 N. 0.2 it is a 0.24. 0.24 N. I am very sorry. 0.24 N. 0.24 N. Sorry. So it is 0.24 N over 0.62 N. Is what? How much it is? 0.39. And last line is what? What is the XAPS? Obviously, XAPS is 1 minus XAP is 0.61. Also is what? What is XAPS? NAPS is how much? 0.38 N. 0.38 N over 0.24 N plus 0.38 N. Same. Okay? This is the answer. To last part. So problem 1 is over. Okay, very good. Anything else I wanted to mention or I forgot to mention? No, it's okay. Very good. Very good. Over. Okay. So remove this. Let us remove this problem. Okay. Remember, these problems are taken from D.R. Gaskell's, okay, book, 2nd edition, page number 408. Okay. Introduction to Metallurgical Thermodynamics. Later on, this book, the subsequent edition, name changed to Introduction to Thermodynamics of Materials. Okay. Well, up to 2nd edition it was this. So sorry. Problem 3. I'm very sorry. Problem 3. Sorry. Okay. Remove this. Remove this. This solution all remove. This is over. Over. Remove this. These are all over. Okay, except this is all over. Unnecessary. This problem 2, okay, is better I actually, so I want to remove this now. This one, here, remove this. Problem 2. What it says, let us read this problem first. Gold and silicon. Acha, write this. Problem 2 solution. Solution. Quickly. Let us read this problem first. Gold and silicon are mutually insoluble in the solid state, okay, and form a binary eutectic system with a eutectic temperature of 636 Kelvin and a eutectic composition of X silicon is 0.186 and gold is the balance, which is 0.814. Calculate the integral molar that I have added actually in bracket, that is, it was written actually in free energy, but integral molar free energy of the eutectic melt relative to, first 1 mole I have added, but unmixed liquid gold and unmixed liquid gold and liquid silicon, unmixed, and B is 1 mole of unmixed solid gold and solid silicon. This actually you have to solve this problem. So this better I draw this gold and silicon. Silicon has a high melting point. Draw the diagram, otherwise you will not be comfortable. Okay, so let me draw the diagram. This is eutectic diagram. No big deal. No big deal. Okay. So how much it is? Okay, eutectic. Huh? So this is sorry. Okay, this is liquid as usual. This is your gold, low melting, silicon is the high melting, this is the temperature. These are given in terms of, okay, note Kelvin. What is the temperature? Eutectic temperature is 636. So this is 636 Kelvin. Okay. This is actually X silicon. X silicon as usual goes to 0, 1. X silicon moves from 0 to 1. So write 0 to 1. Just in case we will revert this one. This is the eutectic potential. Composition is what? 0.186. Oh, this is given. X silicon is how much? 0.186. X silicon. So it is better you write here X silicon eutectic composition is this point. Eutectic composition is what? X silicon is 0.186 and X gold, the balance, is 0.814. These are given, and eutectic temperature right here, composition eutectic temperature is this temperature, 636 Kelvin. Okay, so what you have to find is okay. So very good. You have to, you want to level this liquid plus what you will have here, tell me, plus silicon solid, pure solid. And here liquid, this is right here, this is liquid plus gold solid, liquid plus gold solid. Okay, that is liquid plus silicon. This is gold plus silicon. Eutectic diagram, binary diagram. So first of all, you want to get this, calculate the integral molar free energy of the eutectic melt So we start this. Free energy of the interacting metal relative to something. Relative, we are coming to this. Actually, so G gold silicon eutectic solution. The solution, it is 1 mole molar. So what this is, what is actually relative to minus, follow relative to what? First A. You are answering A. Relative to what? 1 mole unmixed liquid gold and liquid silicon. So what is that? XU unmixed. What is the relative to that? So you should write here G AU 0 unmixed plus X silicon G silicon 0. Okay, this is a pure liquid, unmixed liquid. So this right there, pure liquid. Okay, and give a bracket here. This is perfect. This is your third bracket or single first bracket. It's okay. So this you have to find. Relative to means minus. This value relative to this is minus. Example. 8 relative to 2 is what? Is 8 minus 2 is 6. A certain quantity is A. Relative to A by itself is A alone. Relative to B is what? A minus. Okay, relative. So the minus. This is what? This is to be found. The problem is find this. This part A will be over. Answer this value. But very easy. It looks like a mixing function. Gi bar minus Gi 0. In fact, mixing actually. But anyway, you better do this way. G. What is this? You know, X gold 1 mole. So more fractions will be involved. G and the liquid eutectic solution is liquid solution. This is liquid solution actually. Plus, tell me 1 mole. How you get this? X silicon, G silicon. This is the G. Gi is G, X A Ga bar plus X B Gb bar. G is X A Ga bar plus X B Gb bar in the binary AB. AB is here, gold and silicon. So this you can give a bracket here. Again, once repeat this. XU plus X silicon, G silicon 0. Okay, happy? Take XU common now. XU obviously you are used to this. XU GAU bar liquid minus GAU 0 liquid. Remember, careful, now it is liquid. It's part B, it will be solid. Part B, it will be solid. This to be unmixed solid. Yeah, okay. So now liquid, let us complete this. What I am writing? XU. And give a bracket here. Minus plus XI GSI bar liquid minus GSI bar 0 liquid. This is our famous GAU bar minus GU. This is actually famous is what? Known as GAU bar main. Okay, what is this? XAU, I'm sorry, XAU, this GI bar minus GI 0 is RTLN AI. Recall this, GI bar minus GI 0 is GI bar N, and that is RTLN activity of I. So this XI RTLN activity of gold with respect to pure liquid as a standard state. Is it minus GI 0? Pure liquid, this is very important. Minus what? GI bar GI 0. GI 0 is made of what? Pure liquid. Or liquid state. So with respect to liquid standard state. Pure liquid as the standard state. Pure liquid gold as the standard state. Activity of AU, yeah, in this state, okay. So in this state, okay. So this is very good. This is the eutectic solution, okay, in this state. So this is activity of gold with respect to pure liquid as a standard state, because this is here, plus XSI RTLN activity of silicon liquid. Okay. Now about this, how you get this? Again, this you will get how? Gold liquid is okay. Okay, very good. Very good. Achha, this is okay, very good. Achha, here before I proceed, data given. What is data? This is better. T melting point of gold is what? 1336 Kelvin. And delta H melting gold, enthalpy of melting gold is 12,760 joule. Now here this side other one, PM silicon is what? How much? 1683 Kelvin. Delta HM silicon is how much? 50,630 joule. This will be useful. You can write this, silicon is 1683. And this gold is how much it is? 1336. This will not be used, but this is 13. 1336 Kelvin. Okay, these are data given. This will be useful. I have to forward to this. Now tell me, what is this? Now tell me how to get activity of gold liquid. One thing, very easily you can answer. Of this, remember your focus is here. This liquid is given here. A composition is given here. A quantity. This liquid, about this liquid. Questions about this liquid. The question is what? Activity of gold in this liquid with respect to pure liquid gold as a standard state. Now I tell you what, you can easily answer one thing, but that will be too easy to accept. Or say that is actually not very pragmatic. What is this? I tell you. You first answer the activity of gold is nothing but the mole fraction. It's nothing but the mole fraction of gold, Raoult's law, ideal solution. If this is ideal solution, this liquid is ideal, then activity is gold, mole fraction. Activity of gold is mole fraction of gold. And what is the mole fraction of gold? Is actually here I have given 0.814. And what is the activity of silicon? Mole fraction of silicon is 0.186. So, and RT is everything is known. R is 8.314 and T is this temperature. About this temperature, this eutectic temperature. Calculate the relative to this at this temperature, because this is the temperature is given here, eutectic temperature, eutectic composition, liquid, etc. etc. No problem. But this will be PhaseRule or very is actually oversimplification, because we are not sure that liquid phase follows Raoult's law. This liquid is an ideal solution, we don't know, it is not given here. If that were given, this problem would be very easy, because everything we know. But that is not given. So what we will do? We use to this. You follow this now. So we are going to find this. Two separate exercise. I am doing this. Now to find quickly RT ln AU liquid, okay, and RT ln A silicon liquid. Quickly take one by one. A moment ago I have shown you what is this. Tell me. RT ln AU liquid is nothing but G0 solid minus liquid. Remember, G0 gold solid minus G0 gold liquid. This I told you. Remember, the third bracket. Perhaps remember. Gi bar is Gi bar, etc. A moment. Last problem. Refer to this. Okay, and you know this. RT ln AU solid. This is known as what? This is known as what? Minus solid minus liquid. Liquid minus solid is melting. So it is negative melting. Delta G0 melting. Yes, that you know also. This data will be useful for this. Coming to this. And what is this? This is most. Most crucial, I would say. What is this value? This is very easy also, because this is the same thing. What I said, if you know the activity with respect to one standard state, you know how with respect to the other standard state. Do you know with respect to this? At this composition, tell me, this liquid is in equilibrium with what? This liquid is doubly saturated with gold and silicon. Pure gold, saturated means it is in equilibrium with, this liquid is in equilibrium with gold, pure gold solid, and pure silicon solid. Liquid is in equilibrium. So if the liquid is in equilibrium with gold, so one by one, gold solid, then what is the activity of gold, pure gold solid with respect to gold solid as the standard state? This is with respect to gold solid as the standard state. And since solid gold with respect to solid gold as the standard state is the one. So what is the activity of gold solid in the liquid? Since liquid and gold, so same activity with respect to the same standard state, same activity. So this activity of one actually applies to the liquid also. So the liquid has an activity of gold with respect to liquid as the standard state and solid as the standard. With solid, the answer is easy, because it is in equilibrium with pure gold solid. So this is one, and the whole thing is like last time. So only remains this one. Then you can find out what is this delta G0 right here. Now this is take up exercise. What is the delta G0 melting gold? I taught you other day is what? Delta G H0 melting gold 1 minus T by T melting gold. In the last problem also, I think, I'm sure in the last problem also we did this. Yes, we did this actually. Maybe actually, maybe, but anyway, in case this you can, you know, last class I told you this, okay. Then if you, how to get the delta G melting, if you know the enthalpy of melting and the melting point, and this is the relation, it comes from, okay, see, this I discussed, okay. Explained before means last class, explained before. This I can give you, okay, delta S0, last, this is delta H0 minus T, delta S0 is what? This by this. Because at melting point delta G0 is 0. This is, see, this, recall this, how will you recall this? Assume this will be used, I'm showing you, I'm removing this. Delta G0 like this, delta G0 melting gold, melting, gold, forget. Melting is what? Delta H0 melting minus T delta S0 melting. See how I am getting this. Checking, okay. So what temperature are considering? At temperature melting point. Any temperature melting point, when T is Tm, this is also Tm. This becomes Tm. This is Tm. This is what? At melting point, solid liquid have the same pH and difference is 0, or what you are getting? Oh, I am sorry. Actually, I should have. I should be back to T. Delta is okay. Don't write this. When T is Tm, write this way. T is Tm, what is this? T is Tm, this is 0, left hand side is 0, delta H0 melting Tm minus Tm, delta S0 melting Tm. This leads to what? This side delta S0 melting Tm is nothing but in terms of enthalpy is what? Delta H0 melting Tm by Tm. Okay, put it back into this. So what you will get? Then delta G0, don't cancel this. Delta G0 melting T, I am writing melting T, right? This is what? Delta H0 melting T minus T, delta H0 melting is what? Delta H0 melting Tm by Tn. What you are getting from this delta H0 melting common? Tm is actually at T is Tm. Okay. Actually, this Tm, I am removing this, is making confusion because T or Tm does not make any difference because we know we considered in this thing here delta Cp is 0, so temperature does not matter, so it is unnecessary. Here delta is 0 melting, this will good, this is okay. So now go delta is 0 is delta T is Tm, delta is 0 melting minus Tm, the T must be Tm here, okay, by Tm. So what you are getting here, delta is 0, this Tm unnecessary by Tm. What is this delta is 0, this T, you don't have to write. Delta is 0 melting, because we consider delta Cp is 0, so T or Tm does not matter in case of delta. So this delta is common, 1 minus T by Tm, famous relation. Short.
1 hour 40 minutes.
Oh, sorry. Here actually this is function of temperature. So here because T is here. So this you maintain, this retained. How many? Hello?
1 hour 40 minutes got.
Gone? 20 minutes left?
Hmm.
Oh, it's okay. Thank you. So this is the relation. This I have written here. Remember, I will not repeat this. I have repeated a number of times, multiple times previously. These I have repeated. I will not repeat so many times. Okay. Please remember this. These I have written there. Okay. And what I have added here? This is actually at temperature T. You write this at temperature T. And gold I have added. Gold. Melting point of whom? Gold. Of gold, of silicon. This I have to write T. Okay. I'll remove this. So now, what is this value then? Tell me, what is this value? Delta H gold is how much? 12,760. 1 minus T. What temperature we are discussing? This is what temperature I am discussing. Temperature 636. 636. What is the gold melting point? 1336. Please do this calculation and you will get delta G0 melting is how much? Actually, this is okay. Well, 760, 1 minus 60 is okay. 6686. We check this. 6686 joule per mole. You can give this joule per mole, right? Always 60. This is so substitute this here. Okay, this you substitute this. Okay, and T is what temperature we are considering this. Okay. So this is actually, you write this, so minus delta J melting is what, how much it is? Minus 6686. Okay, so delta G0 melting of gold, at what temperature? At T temperature, T is what? T is here, T is 636. T 636. I am writing this also for, here also I will use 636. Okay. So this is T is 636 and this is also T means 636 means the same. Okay. No problem. 686 or what? R is how much? 8 point, sorry. Right. Quickly. Or 8.314 temperature is what? 636. This better I show this. Ln gold liquid. Oh, no. What I'm doing? Unnecessary. Don't have to proceed more. Okay, joule. RTLN, joule per mole per plane. Joule per mole. Okay, joule or simply joule or joule per mole. Okay, 6686 joule. Keep it here. So this part is over. Is it? To find this one and this one is over. Similarly, RTLN activity of what one? Silicon. Exactly similarly, write this is G0 silicon. Just copy this. Silicon solid minus G0 silicon plus RTLN activity of silicon solid with respect to pure solid silicon as a standard state, and it is pure solid silicon is in equilibrium with liquid. So they both have the same activity with respect to the same standard state. Suppose pure solid silicon is the standard state, so solid silicon has the activity of O1 and liquid is also has the same activity of O1 with respect to solid silicon as the standard state. Okay, so this is, I am very sorry. I am so sorry. Yes, no, it's correct. Solid silicon has the standard state. So yes. So yes, this is unknown. This is known because it is in equilibrium with solid silicon, pure solid silicon, for which activity is 1. So liquid has also the same activity 1 with respect to pure solid silicon. This S means pure solid silicon is the standard state. So this is 1 like last time. So whole thing is 0. So this is minus delta G0 melting silicon. Please do this. Here will you, this is the second problem I am discussing. So it is similarly, where shall I write? Where shall I write? I shall write here. Yeah. Similarly, here. I don't have space. It is better I write here. Right here. From there. Similarly, we will do this. Delta G0 melting silicon. Right. Delta G0 melting silicon at temperature T. Temperature T, incidentally, T will be 636, which I will use here also. Yeah, I have used this. Okay, 636. Okay, so T is what? How much? Delta H0 melting of silicon 1 minus T by T melting silicon. Okay, like last time. What is the delta H0 melting silicon? Is better 5630. 630 1 minus T. What is the TM silicon? 1683. 6883. Okay, and what is the T? Temperature is eutectic temperature 636. At this temperature, what is this? We are writing this for given temperature T. So that's why this T, but T is 636. So put this. Okay. So delta G0 means this is a function of temperature. Remember, this is a delta G0 is always a function of temperature. Delta H0 may not be function of temperature or maybe approximately independent of temperature if delta Cp is 0. And similarly, delta is 0 also, independent of temperature. Kirchhoff's equation. But it is never. So because T is always there. Now this T incidentally, what temperature we are considering? 636 is the temperature. So this is 636. So this T is 636. Okay. Delta 0. So this T 636, this is implied where? Here delta G0 melting is where you have used this. Yeah. This T is, you write or don't write, it is 636 means T. Okay, here, this T. So this value is this value. How much it is? Write this. 50, 60, 30, 1 minus 31497. Oh, it is write this. Please write this 31497. 31497 joule per mole. Per mole. You this put in bracket. This should be here. Now continue. The one you have finished. This next one is here. Here, what value you will give this? See, delta melting is how much? Silicon T implied here is what? This is so minus of this 31497 joule per mole. Okay, joule per mole. So what is this? Then your answer is here. Remember, the answer is here. So hence, write G gold silicon. Write the first line. Eutectic solution 1 mole. Eutectic solution, eutectic liquid solution. I am just copying what I wrote. Eutectic liquid solution means this one. This eutectic solution, liquid solution. Okay, here. So is what is minus with relative to as given in the problem A of minus XAU GU AU0 liquid plus this I am writing top line XSI GSI 0 liquid top line is what? What is it? Here you are here. XA X gold RT-ln activity gold liquid is how much? Answer 6686 negative. See 6686 minus 6686. Then what else? Plus X silicon. Plus X silicon. What is this value? RT-ln activity silica liquid is how much? 31497 minus 31497. X gold is how much? You already have seen. X gold is what? X gold 0.814. 0.814. And X silicon is how much? 0.186. X silicon, how much it is? 0.186. How much is total is, if you do this, let me check, it is minus 6686 plus 186 minus 31497 is what? Minus 111300 joule answer. For 1 mole, this is for 1 mole, 1 mole. 1 mole, or if it is given 1 mole, then just joule. Eh? So 1 mole or mole answer. Since you are considering molar, 1 mole, yeah, so you may give at the end, no problem. Okay, this is the answer. So first part, A is over. A. B will be what? B will be what? I'll do it quickly. B, okay? A is over. Okay. Anything else here? So this part, this will go here, and this star, this one, this box will go here, and this is continuous. RT-ln, see, repeat. This minus this, value of this relative to this minus gives rise to X gold, RT-ln activity gold liquid plus X silicon, RT-ln activity of silicon liquid. To find RT-ln activity gold liquid, how? Through this connection of standard states, change of standard states, relation, standard relation, this relation. So means if you know with respect to this, you don't know, but you know with respect to solid, pure solid as a standard state value. Then you connect them through the melting point. Enthalpy, negative sign, because if you do this, so then this is 0, because activity of with respect to solid gold, pure solid gold 1, activity is 1, and so this is 0. So this value, RT-ln activity gold liquid is minus 6686. Similarly, RT-ln activity of silicon is also likewise. Both are. This liquid is saturated with, we say liquid is saturated with, at eutectic point, liquid is saturated with pure A and pure B, means pure gold and pure silicon. Or in either say saturated with, you may this, or you may say that liquid is in equilibrium with gold. Yes, this liquid is equilibrium with pure gold and silicon at this point. Liquid, gold, and pure gold and pure silicon. So activities are there, pure gold, pure silicon, solids are activities there with respect to solid gold as a standard state. So that will apply to the liquid also. But with respect to liquid as a standard state, then that you have to use this type of relation and find out. And you have found out, this is the answer. So second part is very easy. I'm writing B, just B. What change you will make? What change? See, everything is okay. Relative to has changed. 1 mole of unmixed solid gold and solid liquid. So these remain same. Relative to has changed. What has changed? Solid. What has changed? Solid. Okay? If it is so, then what you will get here? Then again, like last time, liquid minus this is solid will come this side. Oh, sorry, X. Oh, this is it's okay. It's okay. It's not liquid. You can pass. This line is liquid. This is current as before. This is unchanged. First term unchanged. This term changes. Liquid becomes solid. Liquid becomes solid. Continue. See again, right here. Use this side, taking this term gold to the left hand side. Left hand means solid is there, so you come as solid minus, and this one, this side, you take this GSI bar solid. This is plus XSI GSI bar. Now liquid is there left hand side. This liquid is there unchanged, and GSI 0 solid. Liquid is just liquid. This terms changes. This term. So result is this. Now tell me, you have come here. See the change now. See your concept will be clear now. Or if your concept is clear, you will be able to answer. XAU, XAU. GI bar minus GI 0. See the standard state. With respect to pure solid gold as the standard state. The what will be activity of gold? It will be liquid with respect to liquid gold as the standard state. No, this will be changed now with respect to this. This is minus this with respect to this. Solid. And like this side also with respect to solid silicon as the standard state. Now tell me. Now remove this, all remove. Only keep this answer, okay? Answer. Give a box here, answer. Okay, previous one. XSI. Where I am? Yes, I am here. Tell me what is the activity of gold with respect to solid gold as the standard state in this liquid, which is in equilibrium with solid gold and solid silicon. So, and with respect to solid, now it is asked with respect to solid itself. So 1, so 1, and the whole thing is 0, whole thing is 0. So what is this? 0 plus 0 is 0, answer. So give you just answer. The second part is answer is this. Repeat this. The difference, only one difference. Activity of gold with respect to liquid gold as the standard state previously here, and activity of silicon with respect to pure liquid silicon as the standard state. These values are not 0, but we know very easily. If you are asked what is the activity of gold here, liquid plus gold is pure, so activity of with respect to gold means, when I say gold means pure solid gold, this is solid gold, this silicon solid. These are both are solids, remember. Liquid, this is implied. Liquid plus gold means liquid plus gold solid actually. This is solid and this is silicon solid. So with respect to gold solid, gold has solid gold with respect to solid gold has activity of 1. So 1, and solid silicon is pure implied. Solid silicon with respect to solid silicon has the activity of 1. So this is the answer. So now if you want to draw this figure quickly. This for graphical. This is not asked in the question, but graphical explanation. So you try to show this with the free energy of mixing quickly. Free energy versus composition diagram. Recall that versus composition diagram. Remember this? Free energy, what you write here, what is this? XSI moving from 0 to 1. What is this? And you actually, free energy, what temperature you are considering? T is 636 Kelvin. For this temperature, we have this actually. I will draw this. What is this at this temperature below melting points of, so A gold solid. Right, this is the 0. quickly. 0, 0. This is gold solid. 0. I'm sorry. XSI. XSI is 0 to 1. This is gold side. This is silicon side. I'm very sorry. 0, 0. Gold. Free energy of gold is 0. Okay. Solid 0. Okay. Unmixed. This is gold solid. So you write this here. What you want to write this? GSIS is 0. 0, 0. Okay. Very good. And what is gold liquid will be what? Gold liquid. At this temperature, gold liquid has a solid is stable. Solid is the equilibrium phase. So gold liquid will be somewhere here. Somewhere here. Gold liquid. Free energy. You write here free energy. What I write often? Molar free energy. Na? Molar free energy. Okay. Gold solid, this is right. Silicon solid. Okay. Gold liquid here and silicon liquid here. Because free energy is greater than the
2 hours 1 minute.
1 minute. Oh.
27 seconds.
Yes, okay. So unmixed liquid is what? Unmixed liquid? Okay. This is unmixed liquid. This is unmixed solid. Okay. So this part actually, see, this part I will actually explain you next class actually maybe, or maybe let us see. And what is the G of liquid? What is this? Or delta Gm. This is the delta Gm curve. Remember, delta Gm is, this is not ideal solution, so not necessarily non-ideal, but there will be curve, okay, non-ideal curve. If you combine these two, if you combine this and this, you will get this type of. What is this composition? 0.186. Combine this unmixed liquid, G unmixed liquid, What is the, and this is delta Gm. So what is the G liquid is what? This is famous G liquid. And see, at this point, this serves as a common tangent. You have this liquid, common tangent. So it is in equilibrium with gold solid and silicon solid. Okay, common tangent. So this is actually GL. GL. So at this composition, what I said. So what is your value is this actually. These values actually I will next day actually I will explain it. Okay. This problem 2, problem 3. This maybe actually I don't have actually time now. I don't have time now. This is to be explained. Okay. A little more in details actually. A little more detail. So I don't have time. Okay. So but anyway, G liquid. This shows this is the GL. This is actually this will be in equilibrium with. So, but theoretically, what is this? If you take a tangent, this will be G SI bar liquid, G gold bar liquid, and these both are 0. So this 11300 joules actually I will show you next class. Okay, I'm sorry. So anyway, I have to drop this. I'll explain this next class. Okay, with these values actually I will explain this. Okay, next class. Okay, see you these values, this part I will show you next class. Thank you very much for your patience and for your cooperation and for your interest. All these things. See you next class. Bye.